So there's lots of kinds of series. Um, we'll start off, well, we'll continue, remind ourselves about geometric series first. So geometric series, let's look at an example. Let's say we have the sum from n equals 1 to infinity of 2 times 1/3 to the nth power. So we can write out some terms, right? I mean, it's not super helpful, I don't think, but my first term is 2 times 1/3. My next term is 2 times 1 over 3 squared. My next term is 2 times 1 over 3 cubed, forever. And the hallmark of a geometric series is, of course, that each subsequent term is the same multiple of the previous term. So we multiply the first term by 1/3 to get the next term, and this term by 1/3 to get the next term. And always, 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 the ratio is consistent. Here, right, we're multiplying by r equal to 1/3, and the same deal here. So something worth noting is if you're given terms of a series or a sequence and you want to know if it's geometric, one way you can find out is just by dividing the next term by the previous term. And if you do that a bunch of times and it's always the same value, it is a geometric series, and that's your ratio. So like if you divide this by that, you'll get 1/3, and this by that, you'll get 1/3, and so on and so forth. But we would like to kind of figure out what this adds up to and talk about it more kind of specifically. So let's say, suppose we wanted the sum of the first, I don't know, 20 terms. So I'm going to write this out very generically instead of writing out using this particular formula. So my general nth partial sum is going to look like, well, it's my first term, which is sum first term. I said I was going to write that. I'm going to call it A. That's where we usually start. And then my next term is just A times my ratio, and then A times my ratio squared, and then A times my ratio cubed, all the way up to, now this is where things I feel like the notation gets a little bit messy. We're going to have A times my ratio to the n minus 1 power. So I always find kind of annoying, but right, if we're starting at r to the 0th power and you want n terms, you have to end at the n minus 1 term. Right? If you want the first 20 terms, you're going to go either from 1 to 20 or from 0 to 19. That's why we need n minus 1. And then we're going to multiply this whole thing by r. Why? Because I know what's going to happen. Right? Because we're doing the thing that's going to get us the thing we want to see. And so the typical method here is to multiply your whole partial sum by the ratio r. So every term gets multiplied by r. So we get a times r plus a times r squared plus a times r cubed all the way to a times r to the n. And then we're going to subtract these. So if this equals that and this equals that, then we can say the left side minus the left side. So Sn minus r times Sn equals the right side minus the right side. I don't want to write all that out. I want you to observe that if I take all of this and subtract all of this, many, many, many terms cancel out. AR minus AR cancels, AR squared minus AR squared cancels, all the way to A times R to the n minus 1 cancels with the A times R to the n minus 1 that would have been right there. So practically everything cancels when we subtract these. And we're left with A minus A times R to the n. Cool. The purpose of this is to help us find a formula for the nth partial sum. So then we're going to, on the left-hand side here, factor out Sn, the nth partial sum. We're left with, apologies, 1 minus r. On the right-hand side, we're going to factor out the a. We have a times 1 minus r to the n. Finally, dividing by 1 minus r gives us an nth partial sum of 1 minus r to the n over a times 1 minus r to the n over 1 minus r. So in this particular example, it's going to be kind of gross, but if I wanted the sum of the first 20 terms, well, my A is 2/3 in this particular example, right? So here for my example here, my S20 is going to equal my A, which is my first term, 2/3, times my 1 minus my ratio to the nth power, where my n is 20, divided by 1 minus my ratio. I don't love this formula personally. It's not, it feels a little unwieldy, but it is what we need. And then, yeah, you could cancel stuff out. The 2/3 on top does cancel the 2/3 on the bottom. So you actually do end up with just 1 minus 1/3 to the 20th power. I don't know what 1/3 to the 20th power is. It's a big number. Or it's just, I don't know. It's a very small number, actually. It's a number with a very large denominator.
Is that A on the top?
Where is that?
No,
Right here?
no, S is like the.
Right there? That is an A. Yes.
It's on the top.
Correct. It's on the top. Because right, so from here to here, I factored out the A on the right, and I factored out the SN on the left,
Oh.
and then I divided both sides by the 1 minus R to get A times 1 minus R to the end divided by 1 minus R. But the real point here,
And the A times R to the n minus 1 cancels out with the bottom one?
so nothing's can't well in this yeah. So in this particular example, the numbers happen to work out that my A value was 2/3 and my denominator was also 2/3.
Well, I mean, in the where you're trying to derive the normal.
No, the A doesn't cancel out. The A is right there. This is the formula.
On the top, you have of S sub n equals.
That's not that's a that was a
Keep going.
okay. Where?
Like when you subtract the.
This minus this?
Yeah.
Okay.
So the A times R to the n minus 1 cancels out with the bottom one.
The A times sorry.
At the very
Oh yeah. So there's one of these right here. Yeah. So the point of this formula is that if R is in the right place, this nth partial sum will converge. Specifically, here's what we mean. So the limit as n goes to infinity of Sn equal to the limit as n goes to infinity of A times 1 minus R to the nth power over 1 minus R. As long as your ratio R is between -1 and 1, anything that's between -1 and 1 raised to an ever increasing power, if you multiply a number that's smaller than 1 and bigger than -1 by itself, it's going to get closer to 0. So this part right here is going to go to 0, provided that R is between -1 and 1.
What's the difference between big N and little?
I typically use big N for an nth partial sum. There's not really a difference. This is my typical notation choice. Lots of people, I like to reserve little n for like in my summation here, like that. So like when I write this S big N, I'm thinking of this as the sum from n equals little one to capital N of my A sub n. That's why I like to use a big N there instead of a little n, so that I'm not like reusing the little n twice.
Is this S sub n? Is that little n or big?
That should be a big N. Thank you. That's thank you. So this geometric series converges to A over 1 minus R if R is between -1 and 1 and diverges otherwise. On the other hand, so the sum from, sure, I'm going to write it the very generic way, from n equals 0 to infinity of A times R to the n converges or is equal to A over 1 minus R if the absolute value of R is less than 1 is how we usually write that. And this series diverges if the absolute value of R is greater than or equal to 1. So if r is equal to 1, this thing diverges. You get a times r plus a times r plus a times r plus a times r. We're never going to stop. So we're going to get, oh, sorry, if r is equal to 1, we get a times 1 plus a times 1 plus a times 1 plus a times 1 an infinite number of times. So we get infinity. It also diverges if r is equal to -1. So note, if r is equal to -1, you get the sum from n equals 0 to infinity of a times -1 to the n, which is equal to a minus a plus a minus a forever and ever and ever. And the problem here is that the partial sums do not converge. The first partial sum is a. The second partial sum is 0. The third partial sum is a again. The fourth partial sum is 0 again. And this oscillating power just or pattern just repeats forever. And the limit of those partial sums doesn't ever get close to one particular number. And then if r is bigger than 1 or less than -1, we definitely get divergence because the terms are getting infinitely large themselves. Like, for example, if you have something like the sum from n equals 0 to infinity of 3 times 2 to the n, well, you're adding 3 plus 6 plus 12 plus 20, right? The terms are just getting bigger and bigger themselves. If you're adding things, well, in fact, you know what you can do here? You could use the test for divergence, right? Note that the sequence itself, 3 times 2 to the n, the limit of that sequence definitely is not 0. And by the test for divergence, that shows that the series must diverge.
Why are we starting at 0 instead of 1?
Mm, really, because the formula works nicely if you start at 0. So the way I don't actually prefer to start at 0, but generically in the textbook, they usually start this at 0 so that you can write it as a over 1 minus r. I would actually point out that more typically, a nicer version, in my opinion, of this formula is that the sum from, I don't really care where I start, to infinity of a times r to the n is just equal to the first term divided by 1 minus r, which in this case would be a times r to the k over 1 minus r. Again, provided that your r is less than 1 in absolute value. So that's the better version of this formula. But sometimes professors are kind of, I don't know, nitpicky about the way you write this, and people like you just show more work and you say, yeah, I know this cool formula, so you should try to be aware of what your instructor is expecting of you when it comes to the geometric series. Typically with a geometric series, we do, if we're asked about them, we're usually asked, does it converge or diverge? And if it converges, tell me what it converges to. Let's look. Oh, I was going to say something else here. Yeah. Oh, so I was going to say, so since this limit of the sequence is not 0, we can say that the series from n equals 0 to infinity of 3 times 2 to the n must diverge by the nth term test. It is equally valid to say it diverges because your ratio, which is 2, is greater than 1. So usually if you recognize something's a geometric series, you just say it diverges if your ratio is bigger than or equal to 1 or less than or equal to -1. It converges if your ratio is between -1. Now let's see, what else do I have in here? Right. So for example, we could be asked to say, so for the following, determine convergence or divergence and find the value if it converges. We can look at something like the sum from n equals 2 to infinity of 5 times 3/4 to the nth power. And here's what I would say, well, this certainly converges because my ratio, which is equal to 3/4, is between -1 and 1. Or really, you could just write because the ratio is equal to 3/4. I think it's totally right. If you write the ratio is equal to 3/4, everyone knows you know it's between -1 and 1. You don't need to say it's between -1 and 1 if it's obviously between -1 and 1. What does it converge to? Let's see. So this converges to, well, it's going to equal the first term, which is 5 times 3/4 squared divided by 1 minus 3/4. You probably want to err on the side of safety here and simplify anything like this. We can definitely simplify this. Right? This is 5 times 3/4 times 3/4 divided by 1/4 or multiplied by 4 over 1. One of those fours cancels, and you're left with 5 times 9 over 4, or 45 over 4. I'm curious. Yep. On the other hand, if we were given something like the sum from n equals 1 to infinity of, sure, let's do it this way. Sorry, I have to think for a second here. 7 times 3 to the 2n over 4 to the n. Well, first of all, I have somewhat hidden the fact that this is a geometric series. To be geometric, it should be some constant, the sequence should be some constant multiplied by some value raised to the nth power. We can certainly re-express it this way. Yeah, and we should. I'll say another thing as well, but if I rewrite this, I can rewrite this as the sum from n equals 1 to infinity of 7 times 3 to the 2 to the nth power over 4 to the nth power, which is really the same as the sum from n equals 1 to infinity of 7 times 9/4 to the nth power. Clearly my ratio is too big here, right? This diverges because my ratio, which is 9/4, is larger than 1. What if it was really hard to find the ratio, but you were pretty confident it was geometric? Well, you could just start writing out terms. So if we write out if we just start writing out terms here, just to kind of take a look here, this would be 7 times 3 squared over 4 plus 7 times 3 to the 4th over 4 squared plus 7 times 3 to the 6th over 4 cubed. And once you write it a few terms, I think it's easier to see, oh yeah, to get from this term to this term, I definitely multiply by 3 squared on top and 4 to the 1 on the bottom. So I'm multiplying by 9/4. The same is true here. I multiply by 3 squared on the top and 4 to the first on the bottom. It certainly looks like, with my limited information here, that my ratio is 9/4. So sometimes if it's hard to like make the formula look like a thing with a ratio, write out some terms and ask yourself, am I multiplying by the same thing each time to get to the next term? That's your ratio. Let's see, what else do I have to say about this? Oh, sure, we can do that. So one kind of fun, there was something else that just crossed my mind. Oh, I know what it was. Yeah. I remember what it was. I remember last time I said I was going to talk about the telescoping series that I ended class with. Yeah. So before we get there, um, one thing people like to do with this sometimes is they like to ask you to rewrite what's the word I'm looking for? A repeating decimal as a fraction. For example, this repeating decimal, 2.171717 forever and ever and ever, should be able to be written as a fraction because every rational number, every fractional number has a decimal that's either terminating or is repeating some string of numbers. So this can be written as fraction here. So here's what we do. We're going to rewrite this as some fractions added together. The 2 is actually not really important here. 2 is just kind of a red herring. This is 2 plus 17 over 100 plus 17. So this is 17, not thousandths, but 10 thousandths. And this is 17 millionths. Basically, every time you move 2 decimal places over, you get 2 more zeros on the bottom. Or written a better way, it's 2 plus, I'm going to factor out the 17 and multiply this by 1 over 100 plus 1 over 100 squared plus 1 over 100 cubed. Oh, look, I'm starting to see a geometric series. Here's the fun part. You don't actually have to write this using the sigma notation to figure out what it adds up to. We've already, for this part right here, you can already tell me what the first term of that geometric series is. It's 1 over 100. That's the thing it starts with. And you can tell me what the ratio is as well. It's also 1 over 100. That happens a lot, actually. Sometimes the first term and the ratio are the same thing a lot of the time because of the way we often think of these problems. So, but also you could write it as, sometimes you want to write it as the sigma notation. It's the sum from n equals 1 to infinity of 1 over 100 to the nth power. Kind of cool. And then we can certainly say, okay, that's 2 plus 17 times the first term over 1 minus the ratio. So we get 1 over 100 over 99 over 100, which is 1 over 99. This becomes 2 plus 17 times 1 over 99, which becomes 2 plus 17 over 99. And if you wanted to write it as one big old fraction, 2 times 99 over 99 is 198 over 99. So it's 198 over 99 plus 17 over 99, which is 215 over 99. And then if you want, you can check on your calculator just to make sure you did it right. But it should be right. I feel like that's a question people ask a lot. A lot's probably an oversell. Sometimes. I feel like it's more of a good homework question. Okay, so let's look at, oh yeah, I did. So let's go back and look at that telescoping series I mentioned earlier. So last time I mentioned that this telescoping series, the sum from, actually, I'm going to write it a little bit differently than I wrote it last time, just to kind of show you one thing. The little sum from n equals 1 to infinity, let's start at n equals 2, of the natural log of n plus 1 divided by n. I mentioned that this telescoping series is divergent. Well, first of all, it doesn't look like it's telescoping, and often I will say that people try to hide the telescoping nature of a thing to make you look more. I'll in just a second. So basically, telescoping means it's like, so you know, like in a movie where you see like a pirate use like a spyglass and it telescopes out and then it scrunches down to like the beginning and the end. That's what the idea is. Kind of like when we did the subtracting of the previous thing, right? Almost all the terms ended up scrunching down and getting canceled out, and you just have like the first term minus the last term, or the last term minus the first term. That's what a telescoping series is. It's basically all the terms in the middle end up canceling out. Let's see what we mean. So first of all, I have to write this in a way where it actually is telescoping. And the trick here is to remember that we have rules of logarithms. If the natural log of a quotient, it's equal to the natural log of the top part minus the natural log of the bottom part. And then we're just going to start writing out some terms. Now, instead of doing what I did last time, I'm actually, no, I am. I'm going to write out my partial sums. So I'm going to write out the nth partial sum. That's going to be the sum from n equals 2 to capital N of my natural log of n plus 1 minus the natural log of n. So let's see what we get here. So plugging in 2, I get the natural log of 3 minus the natural log of 2. I like parentheses around each term. Plus, now n equals 3. I get the natural log of 4 minus the natural log of 3. N equals 4. I get the natural log of 5 minus the natural log of 4. And then I think it's worthwhile to write out maybe the last two terms. So instead of n, you get capital N, we're going to do capital N minus 1 first. In fact, let's be smart. Here's n equals 2. Here's n equals 3. Here's n equals 4. Here's n equals capital N minus 1. And then lastly, we'll have n equals capital N. So here for capital N minus 1, we're going to get the natural log of capital N minus 1 plus 1, which is just the natural log of capital N, minus the natural log of capital N minus 1. If we plug in n plus just regular n, we're going to get the natural log of capital N plus 1 minus the natural log of capital N. Sorry, it's kind of a squeeze there. Apologies. You can zoom in a little bit so you can maybe try to pretend like you can see that better. But now look, many, many, many terms cancel out. The natural log of 3 and the negative natural log of 3. The natural log of 4 and the negative natural log of 4. The natural log of 5 and the negative natural log of 5 that would have been in the next term that we didn't write down. All the way to the very end, you have the negative natural log of n canceling with the positive natural log of n before it. And this negative natural log of n minus 1 would have canceled with the positive natural log of n minus 1 that came before it. So when you shrunk this all down to the collapsed telescope, you have that this is equal to the negative natural log of 2 plus the natural log of capital N plus 1. Or I would probably write it in the other order. And in this case, my nth partial sum is going to diverge. If we look at the limit as capital N goes to infinity of my nth partial sum, that's the limit as n goes to infinity of the natural log of capital N plus 1 minus the natural log of 2. And hopefully you've seen the logarithm enough times to be like, oh yeah, if my input's getting large, my output also keeps getting large. Even though it's really, really, really slow, the limit of the natural log of n as n goes to infinity is in fact infinity, which means our series diverges. The sum from n equals 2 to infinity of the natural log of n plus 1 over n diverges. And just as a point of aside here, the reason I started at n equals 2 instead of n equals 1, no, I actually didn't have a good reason. I thought I had a good reason, but I was just I think because over here I thought the natural log of 1 was going to be 0, and I just felt like that was kind of silly to start with, but we totally could have started with n equals 1. I didn't really have a great reason there. But it also doesn't matter, right? It doesn't really matter. You could have started at n equals a billion, and this would still diverge. Because what you're saying here, what you would be saying is this sum of an infinite number of things adds up to infinity. If I subtract off the first billion things, which adds up to some finite number, the rest of it still adds up to infinity, right? You can subtract a finite number of stuff from infinity and still always have infinity left behind. That's why it doesn't really matter where we start if you're getting something that diverges. Okay. Let's I feel like I've gotten a little bit behind as far as like things we should talk about. So let's talk about the next thing. And I know I mentioned these before. You know what I should have said? I know what I forgot about here. So before I did any of this, what should I have done? What test should I have thought about using before I tried anything else? Right. So if you take the limit as n goes to infinity of the natural log of n plus 1 over n, what do you get? Well, inside the natural log, but we know how to deal with that kind of infinity over infinity. You could use L'Hopital, but you don't have to. But if you use L'Hopital, you'd have 1 over 1, which is 1. But I want to remind you all, you know this. You just maybe forget that you know it. So let me ask you an easy. So this, I feel like we did this already, but let me just ask you again. What's the limit as x goes to infinity of 3x squared plus 2x plus 1 over 5x squared plus 7x plus 2? Right. You know this. You know that when you have a limit as your thing goes to infinity of a rational function, right, a polynomial over a polynomial, it's always the leading coefficient on top over the leading coefficient on the bottom if the degrees are the same. I asked you the same question. I asked you what's the limit as n goes to infinity of n plus 1 over n? Is that a polynomial over a polynomial? Are the degrees the same? What are the leading coefficients? 1 over 1, right? Don't make it harder than it has to be. Right? Lots of times you're going to have, especially like this thing specifically, like n plus 1 over 1, that limit is 1. But then we have the natural log of that. So it's the natural log of 1, which is 0, which tells us nothing, right? If the limit of the sequence is 0, we know nothing. So we do something else, which is what we did.
Why do we know nothing?
Because this is the test for divergence. So we were asking, does this series converge or diverge? And if you use the test for divergence, the test for divergence says if the limit of the sequence is not 0, then the series
Oh,
diverges. But if the limit is 0, you don't know anything. It could converge, it could diverge. I should say, if the limit of the sequence is 0, the series could diverge or the series could diverge. And there's plenty of divergent series whose sequence has a limit of 0. There's plenty of convergent series whose sequence has a limit of 0. We're going to see examples of them right now. Yeah, so let's look at this fun example. Is this one we're doing? Yeah.
That point before when we used the divergence test, it didn't confirm the divergence.
Correct. Correct. Even though this series does diverge, it is not divergent because of the test for divergence, right? The test for divergence is not showing us that it diverges. We're doing something else to show divergence. Yeah, so the test for divergence and the nth term test are different names for the same thing. They are the same test. The nth term test is the test for divergence. The test for divergence is the nth term test.
Is that
No, I was saying before we did all of this work with the partial sums and the telescoping, whatever, we should have done the nth term test just to check. Right. No, not the same. Those are the same words. You know, like that. What's that meme? Like, show me two things that are the same thing. Like, those are the same thing, right? Pam from The Office, right? Like, those are the same thing. The nth term test, test for divergence, same thing. Oh, so sometimes they'll write. So maybe the options were one was like I'd have to see it really to know. But sometimes they like say it converges by a thing that's like not couldn't ever be true. Like converges by the nth term test can't ever be true. Converges by the test for divergence can't. So maybe they're trying to make it confusing that way, right? You can never ever converge by the nth term test, aka the test for divergence. But I want to make it absolutely 100% solid in your brains. The test for divergence is just another name for the nth term test. Literally, absolutely the same test. Because probably someone came up with it, called it one thing, someone else came up with it around the same time, called it the other thing. I don't actually know that, but like, because I mean, they both make sense for names, right? You are literally using this test to test if the series diverges. You're not testing for convergence, right? You don't get to know it converges using this test. But it also makes sense to call it the nth term test because you're literally asking, okay, if the nth term goes to 0 or doesn't go to 0, then we know the series diverges. So they're both names that make sense in terms of the math that is being done.
What goes to 0?
What goes? So if the nth term does not go to 0, then the series diverges. Okay. So let's look at this next series here. Let me leave that up there. Okay. So let's look at this. You might have seen this already, but it's a very classic example. The sum from n equals 1 to infinity of 1 over n squared, which is 1 plus 1/4 plus 1/9 plus 1/16, and so on and so on and so on. Obviously, hopefully, obviously, the test for divergence, aka the nth term test, is not going to help us out here. Because if you look at the limit as n goes to infinity of 1 over n squared, you get 0. So we don't know anything yet. So the idea here is to look at a comparable value. So check this out. Let me try and sync up here. Yeah, yeah, I'll do this for sure. So we're going to look at the function f of x equal to 1 over x squared. We're going to do it twice. So here's the first picture. Starting at 1, then 2, then 3, then 4. I'm going to use the left endpoint. So this rectangle, even though it doesn't look like it, the base and the height are the same. Right? My base is 1. My height, if I plug in 1 to my function, is also 1. So this rectangle has an area of the first term of my sequence, of my series. This area here is my A1. Right? That's my A1. And then this next rectangle, plugging into my function gives me 1 over 4. So this next rectangle has an area of 1 over 4. That's my A2. And so on. Every rectangle using the left endpoint to find the height is going to give me the next term in my sequence. Now, let me ask you, what has more area? The integral that I've drawn, or sorry, the area under the curve from 1 to infinity, or the area of the rectangles? What's bigger, the rectangles or the area under the curve? It's like the rectangles, right? The rectangles have more. So in this case, we see that the sum from n equals 1 to infinity of 1 over n squared is going to be larger than the integral from 1 to infinity of 1 over x squared dx. In a similar way, but slightly differently, we're going to draw a similar picture. So now we're going to draw the rectangles that are underneath. Whoops, wow. Can my picture look bad? Okay, cool. So we're going to start at 1 here. 1, 2, 3, 4. Same function still. And now when I draw this rectangle, well, this rectangle I'm plugging in 2 to get the height. My height's going to be 1/4. So this rectangle has an area of A2. And this next rectangle is going to have an area of A3. And this next rectangle is going to have an area of A4. So what I could say here is the sum from n equals 2 to infinity of 1 over n squared is less than the integral from 1 to infinity of 1 over x squared. Bless you. And if I wanted to make it so I actually had this integral, I'd add, or sorry, the right summation, I would add on 1 to both sides, or whatever my first term was in general. So if I add 1 to both sides, then the sum from n equals 1 to infinity of 1 over n squared is less than my first term, which is a1 or 1, plus the integral from 1 to infinity of 1 over x squared dx. So very, very broadly, here's what we've got. We've got a compound inequality. This series is stuck. It's stuck between being less than 1 plus the integral from 1 to infinity of 1 over x squared and being bigger than the integral from 1 to infinity of 1 over x squared. So here's what we get to say. If this integral converges, then this series is between it somewhere, and so it converges as well. If this integral diverges, well, then this series is bigger than this divergent integral, so it must also diverge. Or in other words, this is what's called the integral test. If you take whatever series you have and you take the integral of it, if that integral diverges, your series diverges. If that integral converges, your series converges. Or the integral and the series have the same behavior. Well, that's the question. So let's write this down. So the question here is, does the integral from 1 to infinity of 1 over x squared dx converge or diverge? Well, to do that, we use a limit, right? We're going to write the integral from 1 to infinity of 1 over x squared dx as the limit as b approaches infinity of the integral from 1 to b. Instead of 1 over x squared, let's write it as x to the negative 2. We anti-differentiate. We get the limit as b goes to infinity of x to the -1 over -1 evaluated from 1 to b. I really would rather rewrite this as the limit as b goes to infinity of -1 over x from 1 to b. Plug in your limits of integration. You have the limit as b goes to infinity of -1 over b minus -1 over 1, which is plus 1. And then as b goes to infinity, this -1 over b goes to 0. So my integral converges to 1, which means my series also converges. Full stop, period. Not to the same value. So all we know from this work as far as is we know that my series from n equals 1 to infinity of 1 over n squared converges. And we don't really talk about the value, but I'll point out this value is between 1 and 1 plus 1. I will tell you, because it is a widely known fact, that this series actually converges to pi squared divided by 6. But that's probably something you don't actually have to know for this class. There is kind of a slick proof of it that you could all check out sometime if you wanted to. But that's not the point right now. On the other hand, what about the sum from n equals 1 to infinity of 1 over n? Well, what should I do first? You all know the answer. We've said it a lot of times. What do we do first always? The test for divergence or the nth term test, right? Call it whatever you like. Just make sure you know they're the same. So we look at the limit. I mean, again, you don't actually have to write it down. You should do an internal in your brain test for divergence. Does the sequence converge to 0 or not? In this case, yep, for sure is going to be 0. That doesn't help us. But good to have thought of it and made sure that we didn't overlook doing something easy. Because sometimes it will be easy and you'll be like, I should have tried that. Almost guaranteed to a fault, there will be some series on your first exam where if you just remember to do the test for divergence, you'll really easily find the limit of your sequence is not 0 and your series diverges. So that also counts for if the limit of your sequence doesn't exist. Not existing is still not equaling 0. And if your limit doesn't equal 0, your series diverges. End of story. Okay, so this one, we could also use the integral test for. So integral test. So we take the integral from 1 to infinity of 1 over x dx. That's the limit as b goes to infinity of the integral from 1 to b of 1 over x dx, which is equal to the limit as b goes to infinity of the natural log of the absolute value of x from 1 to b. And if we plug in our limits of integration, so limit as b goes to infinity of the natural log of b minus the natural log of 1, which happens to be 0. And as we just said recently, as b goes to infinity, the natural log of b grows infinitely large. So this integral diverges, which means the corresponding series also diverges. So here are two prime examples. One series convergent, one series divergent, where both of their sequences have a limit that is equal to 0. So I'm going to say again, probably lots more times, if the limit of the sequence is 0, you don't know anything. Actually, that's not true. You do know something. You know you have to do something else. That is what you actually should know. If the limit of the sequence is 0, you have to try something else. Sure. So let me just write down the integral test here and then probably should call it a day because I need to try and catch a bus, which is atypical, but my car is getting its oil changed and it's done and I need to get a bus there. So here's the integral test. All you really need to know is that the integral and the series have the same behavior. But here is a few more words about it. So for a positive continuous decreasing function, f of x if a sub n equals f of n, meaning the sequence and the function are the same thing, right? My sequence was 1 over n, my function was 1 over x. My sequence was 1 over n squared, my function was 1 over x squared. The only real difference between the sequence and the function is the sequence has a domain that is just integers, and the function has a domain that's like all positive real numbers usually, or something like that. So if that's the case, then we say the following. One, I'm going to say it this way. The integral from, oh, and I should say for some x bigger than some number n, the integral from f of x dx diverges if and only if the sum from n equals capital N to infinity of a sub n diverges. So it's actually a true back and forth. If the series diverges, the integral diverges, and vice versa. If the integral diverges, the series has to diverge. And similarly, if the integral from n to infinity of f of x converges, I shouldn't say if there. The integral converges if and only if the series converges. Or as I like to say, the integral and the series and the corresponding integral must exhibit the same behavior. They both converge or they both diverge. They do not get to do different things. They're like twins whose parents dress them up the same. They have to do the same thing. No choice. All right, we'll end it a little bit early here so I can go catch a bus.